Biomedical engineer. Biomedical engineers apply engineering principles directly to medicine and biology, building the technology that doctors and patients depend on every day. They design medical devices, artificial organs, prosthetic limbs, pacemakers, and large imaging machines like MRI and CT scanners. The field sits at the meeting point of healthcare and technology, which means these engineers rarely work alone. They collaborate closely with doctors, surgeons, and biologists, translating medical needs into devices that actually work inside or on the human body. It is a relatively young discipline that grew rapidly in the second half of the 20th century, as electronics, material science, and medicine advanced enough to make complex devices possible. A biomedical engineer has to think about problems most engineers never face, like whether a material will be rejected by the body, or how a device can run reliably for years inside a living person without ever being serviced. Because their work directly affects whether people live, recover, or regain lost abilities, precision and reliability are not just goals, but absolute requirements. As populations age and medical technology keeps advancing, biomedical engineering has become one of the most meaningful and fastest growing fields in all of engineering. Petroleum engineer. Petroleum engineers focus on locating and extracting oil and natural gas from deep beneath the Earth's surface. They design drilling methods, plan and manage extraction sites, and work out how to pull resources out of the ground as safely and efficiently as possible. The profession expanded enormously throughout the 20th century as global demand for fuel exploded, powering cars, factories, ships, and entire economies. The job often takes engineers into remote and harsh environments, from scorching deserts to frozen regions to offshore platforms standing in the middle of the ocean. A major part of the work involves understanding what is happening thousands of feet underground, where engineers can never directly see the rock, pressure, and fluids they are dealing with. They rely heavily on data, modeling, and experience to make expensive decisions with incomplete information. Petroleum engineering also carries significant environmental and safety responsibilities, since mistakes can lead to spills, blowouts, and serious damage. As the world's energy needs shift, many petroleum engineers now also work on safer extraction techniques, reducing environmental impact and supporting the gradual transition toward cleaner energy sources. Nuclear engineer. Nuclear engineers work with nuclear energy and radiation, one of the most powerful and tightly controlled forces humans have ever harnessed. They design and maintain nuclear power plants, manage reactor safety, handle radioactive materials, and develop uses for radiation in fields like medicine, research, and industry. The discipline emerged in the middle of the 20th century, born directly out of the development of nuclear power and nuclear weapons during and after the Second World War. In this field, safety is not one priority among many. It is the absolute center of everything, because the consequences of a serious mistake can be severe and last for generations. Nuclear engineers spend much of their time designing systems with multiple layers of backup and failure protection, planning for events that may never happen but cannot be allowed to. Their work also includes the difficult long-term problem of managing nuclear waste, which can remain dangerous for thousands of years. Beyond power generation, nuclear engineers play a major role in medicine, where radiation is used to diagnose and treat diseases like cancer. As the world looks for low-carbon energy sources, nuclear engineering has returned to the center of global energy debates. Structural engineer. Structural engineers specialize in making sure that buildings and structures can stand up and, just as importantly, stay standing. While their work is closely related to civil engineering, their focus is much more specific: the strength, stability, and load-bearing capacity of a structure. They calculate exactly how a building will respond to its own weight, the people and equipment inside it, strong winds, heavy snow, earthquakes, and the slow effects of time. Every skyscraper, stadium, large bridge, and tower relies heavily on structural engineering long before construction ever begins. A structural engineer has to imagine how forces travel through a structure and find the path of every load down to the ground, making sure no part is overloaded. They also have to plan for rare but extreme events, designing buildings that can survive once-in-a-century storms or major earthquakes without collapsing. Their calculations are often the invisible difference between a structure that quietly serves for 100 years and one that fails catastrophically. Because the stakes are so high, structural engineering is governed by strict codes, heavy testing, and careful professional review at nearly every stage. Marine engineer. Marine engineers design, build, and maintain the machinery that powers ships, submarines, and offshore structures. Their focus is on the engines, propulsion systems, fuel systems, and onboard machinery that keep a vessel running reliably far from any port. The field is closely tied to naval architecture, which deals with the design and shape of the ship's hull itself, while marine engineering concentrates on what makes the vessel move and function. Marine engineering has existed for as long as powered ships have, evolving steadily from early steam engines to modern diesel, gas turbine, and even nuclear propulsion in some vessels. A defining challenge of the job is reliability in isolation, because a ship in the middle of the ocean cannot simply pull over for repairs. Systems must be robust, and engineers often have to fix complex problems with whatever is available on board. Marine engineers also deal with harsh conditions like saltwater corrosion, constant vibration, and extreme weather that few other machines ever face. As global trade depends almost entirely on shipping, marine engineers quietly keep one of the most important systems in the world economy moving. Agricultural engineer. Agricultural engineers apply engineering to farming and food production, working to feed a growing world more efficiently. They design machinery, irrigation systems, drainage, grain storage facilities, and the processing equipment used to turn raw crops into food products. The field became increasingly important as farming shifted from small-scale manual labor to large mechanized operations capable of feeding entire nations. An agricultural engineer might develop a more efficient harvesting machine, design an irrigation system that uses far less water, or improve how crops are stored so less food is lost to spoilage and pests. The job blends knowledge from mechanical, civil, and environmental engineering, since farming involves machines, land, water, and biology all at once. Their work has a direct and powerful impact, because even small improvements in efficiency can mean the difference between food shortage and food security for large populations. As the global population continues to grow while available farmland shrinks, agricultural engineers face the enormous challenge of producing more food using less land, less water, and fewer resources, all while reducing environmental harm. Robotics engineer. Robotics engineers design and build robots and automated systems, combining several engineering fields into a single discipline. A working robot needs a body, power, sensors, and intelligence, so robotics engineers draw on mechanical, electrical, and software engineering all at the same time. The field has grown rapidly alongside advances in computing, sensors, and artificial intelligence, moving from simple, repetitive factory arms to machines capable of complex, adaptive behavior. Robotics engineers build an extraordinary range of machines, from the precise arms welding cars on assembly lines to surgical robots that assist doctors with delicate operations, to exploratory robots sent into volcanoes, deep oceans, and other planets where humans cannot safely go. A central challenge in the field is getting a machine to sense its environment and respond to it intelligently, which is far harder than it appears. As automation continues to spread across manufacturing, healthcare, agriculture, and everyday life, robotics engineering keeps expanding into new and sometimes unexpected territory, making it one of the most dynamic and rapidly evolving areas of engineering. Geotechnical engineer. Geotechnical engineers study soil, rock, and the ground beneath structures, focusing on something most people never think about until it fails. Before anything large is built, they investigate whether the earth in that location can actually support it and how the ground will behave over many years. Their work is essential for the foundations of buildings, as well as tunnels, dams, retaining walls, and slopes. The field is closely linked to civil engineering, but its focus is specifically on what lies below the surface, where conditions are hidden and often unpredictable. A geotechnical engineer has to understand how soil shifts, settles, drains, and reacts to weight and water over time, since the ground is rarely as solid or consistent as it looks. Ignoring these factors is one of the most common hidden causes of structural failure, with leaning, cracking, or collapsing structures often tracing back to problems in the ground rather than the structure itself. Because so much depends on conditions that cannot be seen directly, geotechnical engineers rely heavily on drilling, sampling, and testing to make confident decisions. Their careful analysis quietly underpins nearly every major construction project in the world. If you enjoyed this video, make sure to like and subscribe. We have more to cover. See you!